Alright, so for this video we're going to discuss torque. Okay, so we've discussed all the rotational quantities and all the rotational kinematics, and then we identified moment of inertias and rotational energy. And for this one, torque is essentially a force that causes rotation. Okay, so it's fair to think of torque as analogous to force. Okay, and that's pretty much the basic idea. So if I gave you some sort of object, let's just say we just have a stick here filled with some mass. Okay, and we put a rotation point on one end of it. So we're going to refer to this as the pivot. Okay, it's what the whole stick can rotate around. Okay, now to apply a torque, it simply means that we apply a force to this beam. Okay, now you'll see this kind of diagram in your book as well, because it's important to understand that only a certain part of the force can cause a torque. For example, if I push on this with force 1, then that'll cause the entire beam to rotate counterclockwise. Okay, however, if I were to push on the beam with, say, a force 2 that was directed directly at the hinge, this would cause no torque on the pivot. Okay, and so that's kind of that's an important idea. So in terms of these two forces, if I were to think of F1 and F2 as, instead of two different forces, what if these two forces were describing the x and y components of some force? Okay, then it follows that only the perpendicular component of the force will cause any torque. Okay, and so when we say perpendicular, we're referring to a radial line that kind of extends from the pivot. Okay, and any force perpendicular to that radial line will cause torque. Okay, so that's one thing. Okay, now the other side, or the other part of this, is to look at what if I apply torque at an angle. So if I apply this force and I apply it at this angle theta, okay, again, we've just kind of mentioned this, that only this perpendicular part is going to cause a torque. Okay, the parallel component does not cause any torque. Okay, now another thing to think about. So I'm going to redraw this. So we've got the stick pivoted at the end. Okay, so there's your pivot. Okay, now what would be the difference in torque between, say, force 1 and, we'll do this during color, force 2? Okay, so you'll notice that they're both perpendicular to the stick, and so they should both cause a rotation. Okay, but you know intuitively that if you were trying to open a door, right, if this was a bird's eye view of a door, you would know that the further out you go, for the more torque. Okay, so it basically then means that each one of these forces is at some distance, okay, which we'll just label r, because again, it's along some radial line. Okay, and it follows that the torque then has to depend not only on the force that's perpendicular, but also on how far from the pivot you apply the force. Okay, so to put those two things in perspective, that basically means that the torque, and so this is what we use to represent torque. Okay, it's actually the Greek letter tau. Okay, we define the torque as the amount of radius, so how far you are from the pivot, times the perpendicular component of the force. Okay, so the more general way then to say it is you're looking for how far you are from or where you're applying the force from the pivot, times the amount of force you're applying, times the sine of the angle. Okay, and this is the angle between your force and the radius line. Okay, so you can see that, well, if it's at 90 degrees, then torque would simply be just the product of radius times force. Okay, and with this equation, we can kind of see why the torques are going to be different for this second example. All right, the torque applied here for the red radius and force would simply be the product of RF, and then the green one would be also the product of R times F. The problem is, while the F's might be the same, the R's are not. Okay, so because R2 is smaller, but F is the same, then torque 2 should have a much less effect than torque 1 does in rotating the stick. So how much force and how far away you are determines the amount of torque you apply to an object. Okay, so then when we're applying torques to an object, typically you're not going to see just one torque. Okay, you're going to have some sort of object and you're going to apply multiple torques. So for example, imagine a wheel that has some sort of inner wheel to it and the pivot's in the middle. Okay, so say we apply a torque or apply a force downward on this inner wheel. We'll say it has a radius, we'll say just R1, and we apply a force F1 perpendicular to that radius. But then on the outer edge, which is a radius R2, we apply another force, but we're going to make sure it's perpendicular. Okay, so when you see these two forces, then that means that if the axle is feeling the rotation that's trying to occur because of two separate torques. So what we have to then think about is, how do we calculate a net torque that acts on the system? Okay, and net torque is just like we did with net force. It is a sum of torques. So in the case of this one, it would just be R1 times F1 plus R2 times F2. Okay, we're simply adding the torques that are both being applied to the wheel. And for as many forces as we apply, that would be as many torques as we could apply as well. Okay. The only other thing is the directional rotation is still the same as it was with our rotational kinematics. So if a torque causes counterclockwise rotation, then it's positive. Okay. And clockwise rotation would be a negative torque. Okay, so now that we've defined torque, let's look at the next step would be looking at the dynamics of rotation. But before we look at moving rotation objects, let's look at how torque keeps things in perfect equilibrium. We've already talked about equilibrium before, that equilibrium is when things are at rest or they're moving with no net force. So for static equilibrium, this is referring to nothing is happening. There is no movement and there is no rotation. And I'm noticing that it's not writing. Oh, okay, so looks like there's a little bit of delay in the writing to the video. So make sure you pause the video if you need to write down something that just randomly appears. Okay, so again, static equilibrium means that there's no movement, so the net force has to be 0, but there's also no rotation, so there is also absolutely no net torque. So if we want to start with a typical example that you would see, this usually would be something like a sign hanging off a support arm, or some kind of maybe like a flagpole that's standing straight up. Anything that can rotate but doesn't is considered a static equilibrium, because even though there's no rotation, there are other forces that cause motion, so all of these things have to cancel. So we'll do a quick little visual example here involving a sign or a block that's hanging off a support rod. Okay, so we'll say the block has a mass of, I don't know, let's say 25 kilograms. Oh, it's delayed on me again. Okay. Well, the mass of the block is 25 kilograms. The support arm will have a mass of 10 kilograms, and we'll say the support arm is about 2 meters long. Come on, catch up. Any minute now. There it is. Okay. And there's also a cable that would support this rod and block, and we'll say the cable makes a 30-degree angle and is connected to the end of the rod. Okay, so the rotation point for this whole system, if you think about it, if you were to cut the cable, the rod would fall, but it would stay attached to the wall. So we're going to say that the wall is our pivot point. Maybe there's a hinge there or something. Okay, so to get started with this, as the idea with static equilibrium, net force is 0 and torques are 0. So let's start with forces. Whatever forces are on the objects in this system, they have to all add up to 0. So let's identify some of them. The first is a force due to gravity that acts on the block. It has mass, so gravity will try to pull it. The other force, well, the support arm has mass. So it also has a force due to gravity. We'll do that in a different color just so you see it on the picture. It'll catch up. And there we go. Okay. Now we're going to introduce a new type of force. We're going to call this a reaction force. Now, it's kind of easier to understand it in equilibrium as reaction forces. If you want to get overly technical about it, the reaction forces are really the normal force and friction that act on the hinge or the pivot point. But we're just going to call them reaction forces because we don't want to get too technical on recalling normal force and frictions. So we have two reaction forces, one in the x direction, which is pointing to the right on the hinge. It's the wall pushing back. And I'm going to guess a vertical reaction force up. I'm assuming that the weight of the block and the weight of the arm are more than the tension pulling up, so the reaction force on the hinge must point up to kind of help counteract that. And as I just mentioned, there's a support cable, so there's got to be tension in that cable. Hey, the other part to this then, that's really all the forces acting on the system. So now we have to look at each of these forces and ask, well, which one of them causes torque? So any force acting away from the hinge would cause torque. So the tension will cause a torque. The gravity acting on the block would cause a torque. And the gravity acting on the support arm will also cause torque. Each of these forces are acting some distance away from the hinge. Notice that the reaction forces will not cause torque. These are forces that specifically act on the hinge, and so, as we know, forces that act on the pivot point do not cause any torques. So now that we've got our forces identified and all the torques identified, let's start by doing what we already know what to do with forces. Let's figure out what our net force equations are in each direction. So we're going to go back to making our usual force table in X and Y column, and then we'll list out all the forces. So we had a force of gravity acting on the block. We had a force of gravity acting on the support rod. We had a force of tension, and then we had two reaction forces, one in the X and one in the Y. And remember, because this is in static equilibrium then, the net force for both directions must be 0. So let's fill out the table. So for the force due to gravity on the block, that's straight down on the Y, so nothing in the X and negative in the Y. And remember that force due to gravity is the mass times gravity. We also have the force due to gravity on the support arm, nothing in the x, all in the y, and it's negative. Same thing, mass times gravity. Now the tension has to be broken into components. So on the x-axis we would have a cosine of theta, and notice it would point left, so it's negative. And for the y direction we would have tension sine theta, and it's positive because the tension's pulling up. And then the reaction forces, well, their names kind of tell us the direction. The x force is on the x, the y force is on the y, and we have no net force in either direction. So let's write out our equations. In the x direction, we have the reaction force minus tension cosine 30, and those will cancel. In the y direction, we'll have tension sine the angle plus the reaction force in the y minus the weight of the block minus the weight of the support rod. Again, all of these are going to add to 0. Now we also have to look at torques. So let's start with tension. So remember, torque is the radius, or however far you are from the hinge, times the force applied there. So let's look at tension first. So it's going to be some distance away from the hinge. And again, only the vertical part matters, so that's tension sine 30. Well, where is the rope attached? It's attached all the way at the end, so it's at a distance of 2 meters. What about the weight of the block? Well, it's attached at the end, so it would also be 2 meters. And notice the signs. Now the weight of the rod, well, if it's a solid piece in uniform, then the gravity will act wherever the center is, which will be 1 meter. And again, the signs, remember, counterclockwise is positive, which is our tension force, and the weight forces would try to rotate the beam clockwise, so they're both negative. Now we didn't state a question to start off with, so let's just say we're going to find the tension. Now, if you look at the net torque, looking for tension, that's really the only of the 3 equations that we could solve for tension. So if we plug all the numbers in, 2 meters tension sine 30 minus 2 meters times 25 kilograms times gravity minus 1 meter times 10 kilograms times gravity. Now as I go through and calculate these, I know I'm going to write 9.8 because it's gravity, but when I do the calculations I'm just going to round that to 10. So if you crunch these out with your on your own with your calculator and you don't get the same thing, just know that I did 9.8 for gravity. Okay, so let's crunch this out. So the 2 meters and the sine 30 together, that's just equal to 1 times tension, and then 2 meters, 25 kilograms times gravity is about 500, and 1 meter times 10 kilograms times gravity is about 100. And remember, all these are equal to 0, so I just have to move everything to the other side, and we see that tension is 600 newtons. So I know it seems like a lot to write down, but remember, all of the writing is for organization purposes. The actual work involved, the calculating part, is really not that bad. Okay, so now, staying with the same problem, let's find the 2 reaction forces, Rx and Ry. So how much force is pushing on the hinge in the x and y directions? So we'll start with the x force, Rx. Well, that's only located on the net force in the x direction. So now that we know tension, we can solve that pretty quickly. So back to that equation, Rx minus tension cosine 30 equals 0. And if we're solving for Rx, add tension cosine 30 to the other side. We know the tension is 600 newtons times the cosine of 30, and we will get a force approximately around 520 newtons. Okay, so what about the reaction force in the y direction? So let's look at our net force in the y that we had written on the other page. Okay, we started with the reaction force in the y plus the tension at the sine of 30 minus the weight of the block minus the weight of the support arm and all of that is equal to 0. Okay, it'll catch up. Hold on a sec. Come on. Any minute now. Okay, well, all that's equal to 0, and we want to solve for our y. Oh, hey, there you are. So we're going to add the two weights to the other side and subtract tension sine 30 to the other side, and we'll plug in our numbers. Mass of the block was 25 kilograms times gravity. Mass of the rod was 10 kilograms times gravity. The tension was 600 newtons times the sine of 30. So 25 times gravity is roughly 250 newtons. 10 kilograms times gravity is roughly 100 newtons. And 600 sine 30 is 300 newtons. Combine all this and we get that the Y reaction force will be 50 newtons. So hopefully you kind of see, yeah, there's kind of a lot going on here, but the organization is key. And once you have it all organized, everything's just kind of substituting and plugging in, and it gets pretty easy. So let's quickly kind of write out how we would solve these equilibrium problems. So if you look back to what we did in this video, we started off pretty much at the very basics. Draw a free body diagram. Now, even though we didn't actually do a free body diagram, we at least identified the forces on the picture. Okay, and also take note that we identified those forces at the places where they will interact with the objects, and that's important. Remember, when we do torques. And importantly, do not forget that there are these new reaction forces that are acting on the hinge point. Okay, the next thing we're going to want to do after identifying those forces is identify which of those forces causes torque to act on the system. And remember that usually each force that we identified in step 1 will cause a torque, except for the reaction forces. Those forces act on the hinge, and as we know, forces that act on the pivot do not cause torque. Okay, and then our final step for setup is write out your equations. What's your net force in the X, net force in the Y? It's all equal to 0. Write out your net torques. Don't forget about clockwise, counterclockwise directions. And all of your net torques should also add up to 0.